to introduce the Hubbard model from the very beginning to explain the language. Pretty much it's not cutting edge research project I'm going to talk about, but really the basics on how to divide the Hubbard model from the beginning, and then some basic property of the Hubbard model. So it's very basics of the Hubbard model, but let me know if you have any questions. Just stop me anytime. So this is roughly the outline I'm going to talk about today. So first of all, I'm going to talk about generic many electrons problem, what the Hamiltonian we are concerned with. And then I will introduce the second quantization because someone told me they want to be more familiar with the language. Just this is not the language we usually do in the ab initio. And then I will show how to go from the second quantization to a quantum field in continuum. And then when we have the Hamiltonian continuum, we can expand the quantum field in the local Orlean basis, and we will finally get the Hubbard model. And when we get the Hubbard model, I will talk about the symmetry of the Hubbard model. Some known results, some regular results, not so many of them because not so many regular results available for Hubbard model, especially beyond one dimension. Then I'm going to talk about what the limit, especially the strong coupling and the weak coupling limit of the Hubbard model. From that point, you can see one of the main original purpose of the Hubbard model is to investigate the metal insulator transition. You will see it when we study the difference between the strong coupling limit and the weak coupling limit. The other purpose is to try to study a ferromantic sum. So I will also talk about pretty much a mean field ferromantic sum, how to divide the Stoner instability from the perspective of the Hubbard model. And if we have plenty of time, I don't think we may have today, talk about the weak and strong coupling for the anti-ferromantic sum. Of course, this is, again, very basic Hubbard model. You can derive many different physics out of it, but that's roughly the outline I'm going to talk about. Okay, let's talk about a generic many electron problem. So what we're going to talk about is going to talk about a single particle problem. We have the Hamiltonian composed of n particles. Each particle has its own Hamiltonian because they are single particles. They are not interacting. So the Hamiltonian each particle pretty much is separable from the others. And the Hamiltonian is just standard kinetic energy, which is given by p squared over 2m plus the potential energy U. So what is quantum mechanics? Quantum mechanics, basically, the p and x is not Camille. This is all we need to promote the classical Hamiltonian to the quantum mechanical Hamiltonian. In the first quantized form, you write Hamiltonian by replacing the momentum square with the gradient square h bar square over 2m. Pretty much it's just a replacement of the momentum by a differential operator. So they become a differential equation, and what you need to do, or you can see as eigenvalue problem. So you can diagonalize the Hamiltonian and write down the eigenvalue problem. Basically, I have Hamiltonian, I have the eigenfunction and the eigenenergy. So the index here, I just write a k. Not necessarily need to be momentum, but it's just the index for the eigenstate. Now this is single particle Hamiltonian. What we need to do, because we want to do the many particle physics, we want to construct a many-body wave function out of the single particle wave function. The simplest thing we can do is try to anti-symmetrize the wave function. This is the example of the two particle cases. Well, you have two terms because in principle, if the n particle state, you can write it as a n by n determinant because the only two particle, the 2 by 2 determinant just has two terms. That's why we have the orbital 1 with x1 orbital 2 x2, and then exchange between orbital 2 and orbital 1. So this is how you construct a many-body wave function. It basically build it from a single particle wave function, and then the product of the single particle wave function basically, and then anti-symmetrize it because of the fermionic property. So there are normalization factor in front of it, which is 1 over square root 2 because we're on a 2 particle. And the wave function, many-body wave function, capital phi now is normalizable. The energy of the many particle wave function is now just the sum of the single particle eigenenergy. So this is not the most, this is not necessarily the eigenstate, okay? This is only the eigenstate for the system of single particle system. If the interaction here, this is not the eigenstate in general. Any questions so far?
Yeah, I have just one question.
Yeah.
Yeah, so from this antisymmetric wave function expression,
Yeah.
what is the index nu1 and x1 and nu2 and x2?
Yeah, I'm sorry. I should have O as k to make it consistent. It basically the index of the single particle eigenstate.
Okay.
Yeah, you just replace the k by nu here.
Okay.
Yeah.
Okay.
Sorry about that. Okay, I move on. So last time someone told me they want me to introduce it from a second quantized point of view. So here we go. So the idea is in the last page we talked about the particle in eigenstate 1, eigenstate 2, eigenstate 3 labeled by the mu or the momentum k. We can make it more in a more abstract way to say we have a vacuum state. We call it zero ket vector right here, and the zero ket vector mean we have no particle in any eigenstate. So we basically 0 at eigenstate 1, 0 at eigenstate 2, all the way to 0 eigenstate n. Then we define the next step. We define the creation and annihilation operator. So let's say we want to create a particle at state nu. We define this creation operator C deca nu, and what that C deca nu doing is, sorry, I make a mistake. This should be 0 nu, and this is 1 mu here. Okay, so you basically create this should be 0, okay, not 1, and then there should be 1 here. So you create a particle originally empty in a state mu with 1 particle at state mu. And we have a phase vector in front of it because this is fermion, so you swap the particle at 1. You have to anti-symmetrize it. This is the same reason why we need to have an anti-symmetric wave function. And similarly, we define annihilation operator. So we call it C nu. You add on eigenstate with 1 particle in state nu, then you destroy the particle. So it go from 1 to 0. And again, there's a phase vector in front of it because of the anti-symmetric property. Just using these definitions, these two definition equation and annihilation operator, you can divide the commutation relation between them. And this is what the commutation or anti-commutation relation for those creation and annihilation operator. Okay. So now we can go from the first quantized form to second quantized form. If we write the Hamiltonian in first quantized form, the single particle parts is H is given by what we talked about in the first page, basically p squared over 2m, and the interacting part is for some, let's say, 2 particle interaction. It could be Coulomb interaction, so it's somewhat like 1 over distance or other kind of interaction you want to put in the end. Now, how we write the Hamiltonian in the second quantized form? Basically, we just substitute the wave function by the creation and annihilation operator. and the form is given by here. So we have a creation of alpha state and destruction of the beta state with the matrix element given by the single particle wave function symmetry over the single particle Hamiltonian in the first quantized forms. Okay. So similarly, we can write down the interacting part using the same idea, but now the matrix element new here should be new. V here is given by the overlap of 4 orbitals. So how could you solve the first quantized form and the second quantized form are the same thing? Essentially, you just calculate the matrix element in the first quantized form on the left-hand side and the second quantized form in the right-hand side. And you will find that using the definition in the previous page, you will find that they are the same. So you can prove the first quantized form and second quantized form is equivalent. And for the condensed matter purpose, most of the time the second quantized form is just the convenience of the notations because it usually you don't create or destroy particle, not like in high energy theory. So for that purpose, it's necessary to introduce the second quantized form. But for us, the particle is most of the time conserved, and it just a convenient way to write, instead of write down the wave function, we just write down the operator because the operator will take care of the anti-symmetric property. Okay, so we write down the Hamiltonian second quantized form. The next step, we try to write the Hamiltonian continuum basis. And remember that in the last page, we expand the Hamiltonian in terms of the eigenfunction of the single particle basis. And we can change the basis to the local basis. And then after that, we will promote the operator in the local basis to continuum and become a field operator. Essentially, we just expand the local field operator. We define here as psi dagger and psi by the transformation to the eigenbasis. So given by this equation and that equation. And this is a canonical transformation. That means the commutation relation doesn't change. So you end up with the same commutation as you expected for the C alpha dagger and C alpha for the psi x and psi dagger x. It's nothing fancy, just a linear transformation here. Then once we define the psi dagger and x and psi x, we can rewrite the Hamiltonian in terms of them and then promote it in the continuum. Then we find a very simple form of the Hamiltonian in continuum written in terms of the field operator. So essentially, with psi dagger psi with the operator h for the single particle term. Similarly, we have an interacting term with 4 operators, four field operator now. So the next step is how to go back from the continuum to the local Warnian basis. So before we do that, we put back the spin variable to the Hamiltonian first. So we just add the spin. For the non-interacting part, it just sum of the spin up and spin down. For the interacting part here, we just assume the interaction is only density interaction. So we only have 2 spin variable instead of 4. In general, you can have 4 spin variable, but we just assume the interaction is density. It just rewrite the spin, just put back the spin variable in this in the previous equations. So the next step we're going to do is define the local Warnian basis. Let's assume I have a lattice in a one-dimensional chain from orbital 1, orbital 2, orbital 3, orbital 4, orbital 5 to orbital n. Okay. And then this orbital, you can define it on the local locations, have some orthogonal property. So the product of the two Warnian bases we integrate over space, a delta function, and similarly, the same Warnian bases integrate over space, again, delta function in space. So basically, just again expand the field operator in terms of some local bases. So when we do the expansion, then we will be very close to the Hubbard Hamiltonian we want to see. So now this basis become the Warnian basis for the interacting term, and similarly for the kinetic energy term. It's just the same thing as before. We just substitute the eigenbasis for single particle, the Warnian basis. So if we do that, substitute the expansion of the field operator and the Warnian orbital, we end up with this Hamiltonian. It starts to look like the form of the Hubbard model. So the next step we need to do is to calculate the matrix element of this T, R1, R2. So what we need to do is similar as before, again, instead of single particle eigenbasis, this is a Warnian orbital now. And then we calculate this matrix element for Hubbard model. We usually assume that this matrix element decay very quickly, and you can justify it somehow because those are Warnian orbital, presumably is very localized. So R1, R2, if they're very far apart, they tend to decay very quickly. And so in most cases, you just assume they're nearest neighbor or maybe a next nearest neighbor in practice. Okay, some similar thing for the interacting term, but now the integral as a double integral. And here is how you justify the Hubbard model, because the interaction presumably decay very quickly. And again, because the matrix element involve a double integral here, and you can assume the integral decay even more quicker than the kinetic energy term. So that's why the first approximation you can do is just assume this interaction to be only a completely local between the spin up and the spin down at the same location. Of course, in general, you can write down the Hamiltonian with U, which involve 4 different sites, R1, R2, R3, R4, and 4 different spin. But for the in practice, a lot of time we just truncate the interaction to a very short range term, and the justification is because the matrix element decay very quickly.
Ka-Ming, this Warnian function does depend on spin, and I don't remember it depends on spin, didn't it?
Well, we don't.
Then if it depends on spin, you have to depend on spin.
You can put the spin part on it, but usually we don't need to consider it. Yeah, but you definitely can put the spin index on it.
Usually the Warnian function does not should depend on spin, isn't it? Different.
Well, I think depend on whether you have a spin rotational invariance or not. I think most of the time you assume they are. That's why you don't consider it. You just implicitly don't. You don't need to explicitly consider it because they are equivalent for the case you're doing. But in principle, the hopping can be the interaction can be allowed spin dependent.
Mm-hmm.
This interaction can be spin dependent. For example, if you consider the even you consider the interaction, which is Heisenberg interaction, is already spin dependent, even for nearest neighbor interaction. and you have something like you can see a pair hopping term, or even a correlated hopping term, then you will end up with spin dependent.
Yeah. Okay.
But you consider Coulomb interaction in general, no.
Okay.
It's just the most generic form you can write. So we're connecting the term from the previous page. This is the first equation is hopping. Second equation is interaction, truncate all the possible long-range interaction, non-diagonal interactions. Then you end up with this Hubbard term. Basically, just a density operator coupling between spin up and spin down at the same side. And this is the hopping term. So this is everything you can about how to go from the general Hamiltonian to the Hubbard Hamiltonian. So it shouldn't be H naught, it should be H here. Okay, so again, that's very basic. I think most people know about it, but I think I can stop for a minute here and see any questions so I can address it before going on. Okay, no question. So next, I'm going to talk about some property of the Hubbard model. So if we assume the hopping is restricted to the nearest neighbor, the interaction is only local, there are only 3 parameters for this model: the hopping, the interaction, and the implicit parameter density. And if you consider grand canonical ensemble, you can add a chemical potential here, which is equivalent to the density in the canonical ensemble. There's another parameter which is not explicit in the model, is the lattice geometry. It plays an important part. Some lattice geometry can give you very different physics, but without saying anything, we will assume our lattice is either simple square or simple cubic. We don't consider one dimension. Okay, 1D is also special case too. So the next step we want to do is try to investigate the physics at different limit of T and different limit of U, especially for n is close to half filling. Now there's some simple physics you can already imagine.
This n is a total number of particles.
Yeah, or density, yes. Or total
density.
number.
Particle. Okay.
So you can already imagine what kind of physics you are going on a certain limit. For example, if n is very small, so the interaction, the contribution interaction should be quite small, because the electrons don't see each other, the interaction is very local. So you expect will be very similar to the free fermion gas for very low density. The most interesting case is for n very close, well, kind of close to the half filling. Half filling is a special case I'm going to talk about a little bit more. What the most interesting physics going on is when n is not half filling, but slightly away from it. And the contribution of T and U is that for, let me talk about the symmetry first. So there are few symmetry possible in this model. First of all, there are U1 symmetry, or sometimes people call it gauge symmetry. Basically mean if you change the operator C, dagger and C, multiplied by a phase, then the Hamiltonian is invariance. What you mean is, if you rewrite the Hamiltonian by substituting the C by exponential I over CI, C dagger by exponential I over CI dagger, and CI by exponential minus I over CI, then the Hamiltonian will remain the same. This is what I mean by invariance. This is the first invariant, this is a gauge invariant or a charge conservation invariance. The other obvious thing is a spin symmetry. So it's a SU2 spin symmetry, just generate a SU2 algebra. I didn't write it. I only write the S minus here. S plus is just the Hamiltonian conjugate of this. This is a general, very easy to understand symmetry of many models. Pretty much most of the model we just they consider these two symmetry are there, but there's some special symmetry for the Hubbard model for the Hatfield case. The first one is they have another pair of symmetry very similar to the SU2 spin symmetry. It's called pseudo spin symmetry. So the difference between the spin symmetry and the pseudo spin symmetry is there's a phase here. And this symmetry is only remain for particle hole symmetric case or in the bipartite lattice, to be specific, in the bipartite lattice. So the difference is there's a phase in the acting to compared to the spin operator. There's a -1 to the I of a square lattice with I plus J. So there's an additional symmetry. Another symmetry of this model for the Hatfieldian case is bipartite lattice. Is when you repay the annihilation operator by the creation operator multiplied by phase, and the Hamiltonian is also symmetric with respect to it. So that's pretty much all the symmetry you can find in this model. If you're expert on this, this SU2 spin symmetry and SU2 pseudo spin symmetry is not completely independent. So the total symmetry of the model is not exactly SU2 times SU2, but SO4 for slash C2.
Ka-Ming, I have a question. So this the first thing is this -1 to I. This I is the site index, isn't it?
Oh, so this is a complex number. This I.
I know this one, but the
site index. Yes, you're right.
For the SU pseudo spin index, there's a -1 to the I. The I is the site.
Is the site index. If for 1D, let's say.
Okay. Another question is, I can clearly see this U1 symmetry and the particle hole symmetry. That means you transform the creator and the destructor, this transformation. But for SU spin symmetry and SU pseudo spin symmetry, what transformation you're doing?
Basically mean you calculate H, commutator H, comma S, that will be 0. That's what we mean by having that symmetry. So that means S is a good quantum number in the other way to say it.
Oh, okay. So this S or eta are invariant.
Yes.
Okay, not Hamiltonian. Okay.
The state is a good conserved quantum number.
Okay, got it. Thank you.
Mm-hmm. Okay. So very quickly talk about why we are interested in the Hubbard model. A little bit history. The first person who considered the electron crystallization or the localization of electron is regular. If I remember correctly, it would be around 1930, early 30, if I remember correctly. So basically, he just considered the comparison of how the energy change as you change the electron density. The key point is the competition between the Coulomb potential energy will scale with 1/Rs, which Rs is the FA distance of the electron. So roughly speaking, and then you can do the same thing for the kinetic energy. Pretty much you just consider the free fermion energy, and you can solve this for 3D, that is 1/Rs square. And if you compare the competition between the contribution of the kinetic energy and the potential energy due to Coulomb interaction, you can see when Rs change, then the competition between Coulomb, between the potential energy and the kinetic energy also change. When the potential energy is much dominated than the kinetic energy, you leave the think the electron may be localized. This is a conceptual idea how to understand the localization of electron in the early day. So you have very large RS, the potential energy win over the kinetic energy. And then the electron localized, and this is what called regular crystal. You can justify this calculation by simple Hartree-Fock calculation. But the idea is the density of electron play a key role in whether the system is metallic or insulating. So the potential energy win, the electron localize and they ceases to become metallic. So later in the day, the MuST considers similar thing. The difference is calculated, it's still qualitative argument, but he consider a little bit more sophisticated way by consider screening of the electron. The idea is if the screening is very strong, which you expect to happen when the electron density is very large, okay, then the electron is less likely to be bonded to the ion core. Right? The ion core, let's say a positive charge and the electron negative charge. If the charge is not bound, there's no screening, the electron is bound to the ion core, and it becomes an insulator. But if the density of electron get high, it becomes a metallic. Okay, because the screening is so strong. But when the screening it becomes weaker and weaker due to the decrease of electron density, then the bonding, the screening of the positive charge, the ion becomes smaller and electron bound to the ion core. And this is the conceptual idea of the MuST transitions. What Hubbard trying to do is he tried to use that model, the Hubbard model we call nowadays, to understand what we can find for a metal insulated transition in a more quantitative way. That's one of the original purpose for the paper by Hubbard, I think around 1963 and 64. He has 3 papers on this. Basically, all of them deal with the Hubbard model nowadays. The first paper, I think the 3 different paper. The first paper deal with the single band Hubbard model, if I remember correctly. The second paper and third paper deal with the multi-band Hubbard model. And sometimes when you hear people call about Hubbard 1 approximation, Hubbard 2 approximation, Hubbard 3 approximation, they talk about that 3 paper 1963 and 64.
Can you just make a short comment here? I would like to make a short comment, if I may. You know, you mentioned Wigner crystallization and explain Wigner's famous argument. However, I'd like to mention that, you know, this is something that has nothing to do with spin. This is, in fact, you can do it experimentally in the 2D electron gas. You can spin polarize, and there will still be Wigner crystallization because the kinetic and the potential energy scaling has nothing to do with spin. Hubbard physics has a lot to do with spin, and in fact, we can destroy easily the correlated metal with the magnetic through the Zeeman coupling. And so, I mean, I think in some sense, Wigner crystallization is charge ordering, and it is a very different type of process than a MuST transition, which does not necessarily involve any symmetry break. So I think actually, one should keep this in mind. You know, both are interaction-driven effects, but they are not the same type of effect.
Actually, the first, I think, the most clear experimental realization of regular crystal probably is in the quantum Hall event. So it's clearly the spin polarized.
Right.
Okay. Then before I keep going on there, I say I will talk about some regular result. This is pretty much all the regular result you can have for the Hubbard model beyond 1D. The first one, the Lip theorem. The Lip theorem is originally proved for U smaller than 0, which means the interaction is attractive. And theorem say that the ground state you need and always have the spin equal to 0. Now remember, we can have a particle symmetry for the bipartite lattice. If you use the particle symmetry, particle transformation, you can transform the original attractive interaction to the repulsive interactions. So since the theorem originally proved for U is 0, smaller than 0, so the corollary is for U larger than 0, if the lattice is bipartite lattice, the quantum state, the theorem also applies, so the quantum state you need, and the spin is equal to 1/2 A minus B. A minus B means the number of lattice point in the bipartite lattice point A and the lattice point B. Because bipartite lattice, you can write the lattice, well, you can separate the lattice in two groups, the A and B lattice, right? And this is what you have. Let's say you have a simple square lattice, that will be 0 for even number of sides. Another exact result, which people sometimes talk about, but probably it's more academic in most cases, because that may be a singular limit for the Hubbard model. It's called like the Orca theorem. It basically say for U is infinite and repulsive, and you put one hole in the system. Let's say you start from the half filling, you just take one electron out of it. Then the spin of the system will be 1/2 times the number of side minus 1. That means all the this is ferromatic. So again, this exact result, but in practice, it may not be very useful. Another theorem, which also been proved accuracy. So Mermin vector is proved that it is in general true for most cases, but it's actually proved the mathematical accuracy for Hubbard model is that basically saying that no finite temperature spontaneous symmetry working at finite temperature for 2D, and this is also true for 1D at 0 temperature. So if you see the model which tell you that phase transition in 2D, obviously it's violate the Mermin vector. That is in most cases for a lot of approximation. Even you do DMFT, you will always see you will see a transaction, not as a spontaneous symmetry breaking, because you don't put the symmetry breaking theory in the calculation most of the time.
Ka-Ming, for all these three theorems only applies to 1D and 2D. How about to 3D?
No. This is all generic. 1 and 2 are generic, any dimension. 3 is for 2D. There's a no phase transition at finite temperature for 2D, and there's also no phase transition for 0 temperature in 1D. So let's say you do a 1D Hubbard model, it should never have a spontaneous symmetry breaking. It's no true long range order for antiferrometric sum, for example, but you still could have a power law correlation for the antiferrometric ordering, but it's not true long range order. This is what the theorem say. Okay, so finally we have some figure. So say I'm going to consider a limit. The first limit is a U0 limit, which that means phi electron case. So the physics is rather simple. You can diagonalize the Hamiltonian exactly, which just end up with a cosine band if you have the nearest neighbor hopping. And the wave function is just filling up all the possible state below the Fermi level. So you add the creation operator for all the state below the Fermi level EF. What you find is this spectral function. This is just a figure I pull out from this book chapter, which is the density of state at different dimension. The dashed line is the case for infinite dimension. Well, again, people interested in infinite dimension because that somewhat related to DMFT, which Hannah will talk about next week. So the dashed line here is the density of state for infinite dimension, and the solid line is the density of state for from 1D, 2D, 3D to 4D, 5D, 6D, infinite D actually. So you can see the density there. The shape is very different when you go from dimension 1 to dimension 3, but when you above the dimension 3, the shape is kind of closer and closer to the Gaussian. Actually, you can prove that an infinite dimension, the density is perfectly Gaussian. So this is the case for the one dimension. The key point is the system is metallic. That means if you consider half filling, you just fill the system up to the omega 0 here. There's a no gap in the spectral function. Now we consider another limit, which is the T or 0 limit. So we only have a U term. So what the U term do is they just avoid two electrons just sitting on the same side. Right? If they sit on the same side, they will pay the energy penalty U. So the electron just try to avoid each other. So what the wave function you can construct under this constraint is you start from vacuum state, the state with low electron, and try to add the electron to the vacuum state, but provide and make sure there's no two electrons sitting on the same side. So in principle, the wave function has a massive degeneracy because its side can be up or down. So you get 2 to the power L number of possible state with the same energy. Of course, the non-zero T will break this symmetry. If we write down the spectral function for this wave function, this is what you get. So you have one pit, let's say minus U over 2. You can shift the reference energy, but let's say assume this pit is at energy minus U over 2 and another pit at U over 2. So if you have half filling state, all the state will fill up the energy state of minus U over 2, and sometimes we call it lower Hubbard band. And one, you fill up all the lower Hubbard band up to half filling. So you can fill n electron at the lower Hubbard band, but if you have n plus 1 electron, n is the number of site, then you need to fill upper Hubbard band. So you have an energy penalty, you have energy gap when the system is at the half filling. Compare the previous case, go back here, spectral function have no gap at one omega 0 or at half filling. So one of the main question is what the situation change when the U or T, neither of them is 0. So this is what happened from the DMFT calculation. I will leave the detailed handle for the next week, but this is the spectral function module calculator in 1991 by Ka-Ming using a DMFT theory. So basically, he tried to fix the temperature. It's fixed now, it's a finite temperature. Fix the temperature and change the value of U. And you can see for small value of U, they are very high sharp peak at energy 0. And as he crank up the U from 2 to 3, then the peak at the middle become much reduced, and the band at I1 U over 2. I1 U over 2 is setting up at the side. Sometimes you call satellite band or Hubbard side band. And when you crank up the interaction higher and higher, the peak at the side become higher and higher. So it basically interpolation between the situation for U or 0, which is what you see in this figure, and the situation for T or 0 in this figure. Well, subtlety here is the tensor state here is for infinite dimension.
This is a 1D, right?
This is infinite dimension.
Or infinite dimension.
This is DMFT result. Sure, you can also calculate it 1D. I don't want to solve the case for 1D because the subtlety here in 1D. But this infinite dimension presumably very good down to maybe dimension 4. Okay, what is really good for 3 or 2? This up to debate, but this should be quite general, at least up to dimension 4, maybe 3.
So by the way, I want to ask, why do you mention 4 specifically? Why not something else?
It's upper critical dimension of mean field.
But do you think that this is, the upper critical dimension depends on the symmetry of the problem? For the classical Ising model, we know it's 4, but for other problems, it's something else. And for some problems like Anderson localization, it's well established that there is no upper critical dimension.
Yeah, I agree
So
about that. Wow, because in principle you don't know the dynamical exponent. So wow, assume the dynamical exponent is 2, okay, then you can say physical dimension 2, even physical dimension 2 will be a good approximation for mean field. It depends.
Where does that come from? I mean, I don't, if someone asks me how do you estimate the upper critical dimension, I know how to do it when you have a symmetry breaking transition and follow Wilson Fisher method. But other than that, I have no idea how to even determine the upper critical dimension.
Well, yeah. If there's parametric state, yes. And this is parametric state, yeah, to be honest, yes. But there's also a question, well, how could a mean field theory is when you go to different dimension? Then I think.
Well, I've been working in EMFT for a long time, and one thing I've noticed, which has bothered me a lot, that if you do a cluster theory, it has a finite cluster. So in the sense of Wilson, it will still be a mean field theory, and you'll have the mean field exponents for any finite cluster size.
Yes.
So that will not change your exponents, but we know that in DMFT, cluster theories can produce very different results from single site theory. So it's not about the dimension only. It can also do with a form of local correlations and so forth, right? So,
yeah, because
so I think it's an interesting question, which I think deserves more more attention.
Yeah, you're right, because it's not close to a critical point. Then you get very different physics. Okay, to be very precise, okay, this concept of critical dimension only makes sense when you are very close to the critical point. Right? When you're away from the critical point, this thing doesn't make any sense at all. So, yeah, but the idea is the main idea is try to solve what the difference of interpolate between 2T0 and U0, and this is one example for the infinite dimension calculation from DMFT. So I think that will be the last thing I'm going to talk about, because when you introduce a Hubbard model, sometimes you want to introduce the theoretic sum in the Hubbard model, because this is another reason to study the Hubbard model. Essentially, I want to reconstruct what the Stoner instability is. You simply try to decouple the interaction term. Here's U, NL up times ML down. It's just a standard Hubbard interaction term, and you try to factorize it and have a mean field theory. So you rewrite the interaction term as a magnetization. So basically NL up minus NL down, and then you try to do mean field of this term, and you define the magnetization basic expectation value of NL up minus NL down. Rewrite the Hamiltonian by the mean field approximation, and the Hamiltonian here become quadratic, so you can calculate the energy exactly in terms of the magnetization, and this is the result. Just go through the step of calculation, you get the result, and you can find in what circumstance the M should be non-zero, and in this case the M will be non-zero, just to compare these two terms. So you get the condition for this to happen, for M non-zero to happen, is U times the density of state is greater than 1, and which is what you learn from the Stoner instability. So just to show you one of the example, you can pull out something familiar from the Hubbard model. Of course, you can do the same calculation for the anti-ferrometric sum. You can also do the mean field for the superconductivity. You can also try to find pairing stability in the model. So that pretty much I want to talk about today. The next step I can maybe talk about the strong coupling limit anti-ferrometric sum, which you end up with the Heisenberg model, and then how the Dr. Heisenberg model become a TJ model and the physics on that. But I think I will stop here today.
Okay, thank you. Let's ask some questions. So it's a Stoner model. The Stoner criteria is not originally derived from Hubbard model, right? It just
No.
happened-
It's just an example. You can do that in the Hubbard model.
Yeah.
No, definitely not.
Yeah, I have another question is, you show the solution, infinite dimension solution. Those are exact solution, right? For Q and the T and the picture.
Okay, let be very precise. Okay, since we talk about Bookend symmetry or not, this is the solution. Assume there's no Bookend symmetry at infinite dimension.
Okay.
So this is enforced symmetry. Okay, because presumably you will expect the system to order antifermatically at half filling. Let's say you can write down the exact solution. I believe you will get antifermatic. And there's no proof on it. There's no rigorous proof for antifermatism in Hubbard model, as far as I know. There's proof of fermatism for one hole at U0, U infinity, which is like the Orca theorem. I don't think even have a theorem for any limit to solve the Hubbard model's antifermatic. But you can do any calculation. You can do a weak coupling perturbation theory. You can do a strong coupling perturbation theory, and you will always find antifermatic at half filling. So the model, the data I showed you, assume the system has no such ordering at infinite dimension.
Yeah. So I have a question about how you reconcile or maybe combine the Hubbard model with DFT, because it seems like there are two different languages. You have the for the Hubbard model, you always have the many body wave function. You need to treat the you have the quantum field theory method to treat the exchange correlation, and in DFT you have you always swap the exchange correlation into the functional, and you always have like essentially solving the single particle.
Yeah. So what DFT doing is that let me start from the Hamiltonian. So this is the single particle Hamiltonian, right? What DFT doing is try to find the best value of U to incorporate part of the interaction. So what I mean is that the interaction generically should be this 4 operator term. Okay, but you can do some kind of mean field approximation, just like what I talked about at the page of Stoner criteria, Stoner instability. You can just factorize the 4 operator and the 2 operator term. Then it will be a constant times 2 operator term, like the single particle part, right? And basically, the fundamental idea is how to find the value of your extreme correlation function, which do the best way to take care of the factorizer interactions. Just from a very high, from a very bird's eye perspective. So what is not included is there's some interaction which is not, which cannot be completely represented by this single particle Hamiltonian, and this is what could be missing in DFT. Of course, you have theorem to prove if you get the you can always get a density covariance zero temperature.
Okay, so can I say there's some ambiguity in calculating the U factor from DFT, because
may I add something here?
Yeah, please.
Yeah. So in DFT, you are taking care of correlation through exchange correlation function, right?
Yeah.
And in DMFT, you are also treating like on-site Hubbard interactions. So because of this, there is double counting issues.
Yeah.
So
Just
you
right.
have to, so you have to take care of this factor. So in general, so far in literature, there are three ways you can resolve these double counting issues. So and so these are three ways. So maybe I can talk about later in these three ways detail.
I just want to ask, because I'm not an expert on DFT part of the work. I of course heard about, I'm aware of the double counting problem, and I know that there are different schemes. I'm just curious, maybe it would be of interest to everyone to know, in practical terms, so Wasim, if you use different schemes, what's your feeling? How different are the results? I mean, I know that the numbers come out different, but are there, I mean, how much is known? You know, is there some clear evidence that in some regimes where the three schemes will give you completely different results, so you can really discriminate which one makes sense? Or it's just a question of numbers? And what's your feeling about all this?
From my experience, I did some calculations for a orbital compound and like cerium and all those stuff, and their result changes with this double counting.
Yeah, but how different is this? What's the main, you know, if you pick one or the other, can you give us a flavor? You know, what would be the main difference? Is this just you're going to get, say, bandwidth is, or some gap is going to change by 30% or by 20%, or you will get an insulator instead of a metal?
Yes.
How serious are the problems?
Yeah, so gap changes significantly. Gap changes generally.
And is there a comparison to experiments that can guide you in selecting this scheme?
Yes. So what I have seen gap changes significantly with this three kind of double counting corrections, and you can compare your spectral function with experiment. On that way, you can guide to experiments.
But is there a consensus, you know, that you can apply it to 5 different materials across the periodic table, and then is there one scheme that wins every time, or the agreement with experiments versus scheme is completely a random thing that you cannot make clear sense out of it? I mean, what's, you know,
yes,
what's your feeling?
So far this double counting issues, I think, is not completely resolved yet. So far there is no such studies where people have taken series of materials and did the double counting issues and show that this scheme works better for these kind of materials. So far people have not done yet.
So you're saying there is anecdotal evidence, but there is no scientific systematic study.
Yes, systematic study.
Okay, that's really good to know from someone, you know.
I think it's certainly a good topic that Wasim is going to give us. So let's think about what's the title of the topic. You're going to show LDA plus U or what, or a Hubbard model and beyond, or something like this.
I mean, that's actually a very good question. But another sort of DFT-related question I had was actually, I mean, these comments and what Wasim made are basically sort of related to trying to patch together a Hubbard model for, or in the terms of DMFT, Anderson impurity model and LDA, and subtracting the double counting. Another question is, I mean, you also could formulate DFT for the Hubbard model itself. How does that what is the state of that? How does that compare to more accurate methods?
Is this actually done by anyone?
I don't know.
Oh, yeah, that's a very good point. It's an interesting point. Yeah.
Yes. So within this DFT framework, I mean, people are trying to address the correlation issues like LDA plus U method and those stuffs, but those are still static. There is no dynamic information in those kind of studies. So
no, but I think what Marcus is asking is this. My understanding is separately did the quantum Monte Carlo for for the
so
continuum.
Exactly. I'm not asking about an ab initio DFT like we are all doing, but a DFT, a density functional theory for the Hubbard model.
Yeah, so I'm coming to, how would you do it? I know how you do it in principle for DFT. You do the quantum Monte Carlo and you determine the energy of the system as a function of the density, right? Now in the uniform Gellium model, the density is uniform.
Yep.
So there is a one-to-one mapping between density and energy, right? Correlation energy. You can compute the correlation energy directly, right? Then you assume that the density is locally smooth in LDA, right? So you replace the density, the correlation energy, by the local approximation. That was the basis of LDA, and then there are corrections to it. But the point was that you have to imagine that the density is uniformly changing, and then ask how now how do you do this in a lattice model where you cannot change the density? Well, like in half filling. How would you do it in half filling, right? That's the point. Is that it's not clear to me how, in principle, suppose you could do the diffusion Monte Carlo for the Hubbard model. All right, now how would we construct the density functional theory? I think that's what you're asking. That's an interesting question. No. I don't know how I would do it actually, right? But
and you probably would an LDA itself probably would not make terribly much sense, but if you have some type of a stencil or a kernel to have a more extended kernel to take the neighboring sites into account, sort of more along a type of a GGA or more extended system might be a interesting approach.
Mm-hmm. Yes.
Yeah, it's a very interesting question, but I don't know DFT for the Hubbard model yet. I don't have any idea.
There's also DFT for classical models,
right?
Which where Krishnan and Lusov have done, and that works surprisingly well, in fact, right? So the DFT idea is very flexible and very general. It's not. It's almost magical, so to speak. Right?
Okay. Any other questions? So certainly, obviously, Wasim can give us some another topic you can talk about maybe after Hannah's talk. Maybe you can prepare something about what you have done, LDA plus U.
Yeah, I can talk about LDA plus DMFT methods and how people are doing that.
Yeah. Okay. We'll bring to the discussion. Will be great. Wonderful.
I think this is really important and interesting because there are different views on how this can be done. And it relates also to what Ka-Ming Tam mentioned, the Vannier functions. People used to use just the Vannier functions, but then how you construct them exactly and where do you stick in the U is something very confusing, at least to me, because I come from not from a DFT background and I have a very poor understanding. I would like to understand it better. But I also understand that people who did LDA plus U already had to face that problem, right? They had to answer the question, where do we stick in the U? It's not really about the MFT so much as about where do you put the U, right? And so I know that my friend Christian Haula, he was actually very much inspired by the work done by Anisimov early on LDA plus U, where they have actually constructed a particular way to select local orbitals through projectors. And so this is a broader question. It's not only about the DMFT approximation. It's more about how you write something like an Anderson lattice model or so. I think that would be nice to discuss this because there are different ways. And I think, we've been discussing recently about how we want to put disorder and the typical medium approach. That also will depend on, I think, in some sense, how you do this construction. Yeah. Because the simplest ways to treat disorder are based on localized orbitals. And so, this will also be an interesting question because there may be different views and different ways how you can do it for different applications.
Yeah. So there are various different projection scheme, but you have to make sure after you do the projection, you are not losing anything. So maybe I will talk about detail later.
Yeah. Another thing is, before you talk about LDF plus U, I hope that anybody understand the DFT. First of all, do you think we should have a DFT discussion first before LDF plus U, or if anybody don't understand DFT, then we don't have to do it. But if you,
I think after Hana will give talk on DMFT. So after that we can talk somebody only DFT. Then after I will join.
Okay, yeah, I mean that might be a good idea. Just sort of a basic tutorial on DFT, yeah.
And you also want basic tutorial on DMFT, right?
Yeah.
Okay.
So who want to give us a talk about DFT?
Okay, that'll be either you or me.
You want to do it?
Okay.
DFT, of course, you have to talk about Thomas Fermi also, maybe.
Yeah,
you want to do it?
Okay, yeah.
Okay, good. We have some topics. Then DFT by Marcus and LDA plus U by Wasim. Okay, excellent. Okay, that's excellent discussion, and I hope we're going to continue like this. And if you have any questions, we send an email to Ka-Ming. Then maybe Ka-Ming will spend some 10 or 20 minutes next time to answer all the questions we have today.
Okay, sure.
Okay.
Let me know. Okay, don't be too difficult.
No. We try to get everybody on the same level. Then we can just, because what we're gonna do for the research will help.
If I may mention actually an idea which is more of a long-term idea. In the past I've organized some conferences, and one thing I've done in around that with Nadine Trivedi and Jim Wallace, that we had a conference on disorder and interactions and so forth, and then we decided to ask speakers to provide review articles. We had that little monograph published. It was called Conductor Insulator Quantum Phase Transition. And that was actually, I thought it was a good experience, because many people contributed and you can bring things up to speed. Now, it seems to me, since people are giving pedagogical lectures here and so forth on many topics of interest, one could imagine that over time, these lectures can turn into chapters of a book, which could be written about these general topics, and which will be actually pedagogical and accessible to the reader, but at the same time covering much more than existing materials have. And in particular, I think many people here are also interested in disorder, and I don't think there exists right now such a pedagogical, text, how you combine ab initio methods with correlations, with disorder, how to make it, explain whether the available current methods able to do, whether they're not able to do, allow someone to jump in from the outside. I think that would be really nice. And I think maybe, through this process, one could, there are many people already involved, and maybe one could actually produce, in a year or in 2 years, such a monograph, which could be very popular and very useful for many people in the world, and also bring this group to prominence, and visibility. I think that would be maybe a good idea.
That's an excellent idea. We kind of, I can see down the road we can have a book. That's excellent. Great. Okay, and I'm going to upload this recording to YouTube, and pay attention to if any viewers they have any comments. We may have to engage. Just pay attention to it.
All of you should definitely subscribe.
Yes, subscribe to the channel. Okay. All right. Okay, we'll see you next week. Have a good weekend.
Okay. Yeah. Bye.
Come in.
Bye.
Bye.